From shipwreck recovery to offshore rig construction and heavy marine industries, maritime operations demand precision, strength, and smart solutions in extreme environments. The hot metal crane is a special overhead crane designed to lift and transport molten metal ladles inside steelmaking and foundry plants. This crane usually operates directly above the furnace and casting areas. Therefore, its construction must withstand extremely high temperatures and harsh working conditions. Typically, the crane is equipped with heat-resistant components, powerful hoisting mechanisms, and a reliable ladle hook system to ensure safe lifting of several tons of liquid steel. During operation, the crane operator carefully positions the ladle below the tapping point, then lifts and moves it to the pouring station. Smooth and precise control is essential to avoid splashing metal and to maintain continuous production. In addition, modern hot metal cranes are often equipped with automation features, temperature shields, load monitoring devices, and emergency braking systems to enhance safety. Overall, this equipment plays a crucial role in the steel production cycle, ensuring efficient handling of molten metal while protecting personnel, equipment, and plant operations. This anchoring evolution near Panama shows how the crew manages the anchor chain under challenging conditions. Initially, only 3 shots were planned. However, the brake failed to set properly, causing the chain to run out rapidly. As a result, nearly 600 feet were released before the problem was controlled. When the chain turns red, it indicates only 1 shot remaining, meaning the ship was close to a runaway anchor situation. Meanwhile, the sailor forward waits to raise the Union Jack. Tata Steel produces iron ore for its steel plants through the Noah Mundi and Kanban mines, which belong to the Ore, Mines, and Quarries Division. As the Jamshedpur and Kalinganagar steel plants expand, mining operations are also being upgraded to meet growing production needs. Previously, the mines mainly supplied lumps. However, rising demand for fines encouraged the company to adopt new crushing and screening solutions directly at the mine site. To achieve this, Tata Steel partnered with Metso India under a life cycle services contract that covers logistics, crushing, screening, and final delivery. Metso's specialized units ensure the required product size even with high tumbler index ore and help beneficiate lower-grade materials. Furthermore, the partnership meets high safety expectations and demonstrates strong technical capability. In December 2002, the car carrier Tricolor, sister ship of the Trianon, departed the port of Zeebrugge bound for Southampton. Only a few hours later, in the early morning of the 14th of December 2002, disaster struck in the middle of one of the busiest shipping routes in the world. At approximately 2:15, the container vessel Kariba collided with the Tricolor. The impact was severe, and although the captain of Tricolor attempted a hard starboard maneuver to avoid the collision, it was already too late. Within 30 minutes of the collision, the 190-meter-long vessel capsized and sank to the bottom of the channel. Fortunately, immediate and well-trained evacuation procedures ensured that all 24 crew members escaped in time. The crew were rescued shortly after abandoning the ship, and no human life was lost. Nevertheless, a major maritime accident had occurred. A modern car carrier, loaded with more than 2,000 vehicles, had gone down in an extremely exposed position. When the Tricolor settled onto the seabed, the vessel lay on her port side in a narrow traffic corridor. The wreck quickly became a potential navigational hazard to passing commercial shipping, especially under nighttime or foggy conditions. Moreover, the Tricolor was leaking bunker oil, creating an immediate environmental threat. The location of the capsized vessel was outside the natural shelter of the Flemish banks and fully exposed to wind, tide, and strong coastal currents. That combination accelerated the release of oil and made every offshore operation more complex. The owner's top priority therefore became preventing and minimizing pollution while developing a workable plan for the complete removal of the wreck. One of the first actions was the deployment of the large floating shear-legs crane vessel Asian Hercules II together with empty barges to recover escaping oil. Divers were mobilized to inspect the hull, but they were forced to work under extremely difficult conditions caused by the strong tide, high waves, and the harsh December weather in the North Sea. Although the vessel rested almost entirely on its side, the salvage team designed a method to gain access to the lower tank areas. Because the bottom of the ship was now exposed, divers drilled holes into the submerged tank spaces. Each hole was fitted with a flange to allow sealing afterwards, and then connected by hose to powerful pumps. In principle, the system allowed the bunker oil to be pumped directly into reception tanks on supporting vessels. Over a period of 2 months, more than 100 tons of oil were successfully removed. However, some residual oil remained inside inaccessible compartments near the engine room or trapped across damaged car decks. Although every effort was made, a limited amount of oil escaped into the sea. Even so, the operation prevented far more severe environmental consequences. Once the oil removal phase had been completed, preparations for one of the largest wreck removal operations ever attempted began immediately. The Tricolor measured 32 meters in width and was structurally strong when afloat, but in its overturned condition the hull was far too vulnerable to be lifted in one piece. Uprighting the wreck was also considered impractical due to the position of the ship, the unpredictable seabed, and the immense forces required. After extensive evaluation, the salvage consortium decided on a radical solution. The Tricolor would be cut into 9 large sections and lifted sequentially. To undertake this task, 2 large working platforms were installed on both sides of the wreck. These platforms featured extendable legs that could reach the seabed at a depth of about 30 meters, creating a stable base for heavy operations in open water. This approach had never before been applied to a vessel of this size, and it required the development and testing of specialized cutting technology. The salvage engineer selected a cutting technique based on a specially designed cutting wire. A similar system had previously been used to cut the Russian submarine Kursk, but in the case of Tricolor, far more and larger sections had to be sliced. The cutting wire itself consisted of almost 10,000 hardened cylinders mounted over a steel wire and coated with a material nearly as hard as diamond. Before cutting could begin, the wire had to be passed under the wreck. Divers and drilling teams used flexible drills to tunnel beneath the hull. When the drill emerged on the opposite side, a hollow tube was inserted to serve as a guide for the cutting wire. Large winches then applied enormous tension to draw the wire back and forth, slowly sawing upward through the hull from the bottom. For the first cut, 2 wires were used until the cutting reached the propeller shaft. Every subsequent cut was performed with a single wire. The cutting progressed at approximately 1 meter per second, with forces on the leading end reaching 60 tons and a back tension of over 20 tons. During this phase, diving teams continuously monitored both the wire and the shifting structure of the wreck. The changing tides allowed only short working windows, often no more than 20 minutes of practical underwater time during each cycle. While cutting continued, additional preparation took place to ensure safe handling of each separated section. Large steel lifting frames were welded onto the starboard side of the hull so that cranes could attach multiple lifting cables. In some areas, the water was extremely shallow, making installation of chains, slings, and lifting points especially laborious. Some sections weighed up to 3,000 tons, so engineering calculations defined allowable load at each attachment point. Chains were even installed around the propeller, and a total of 12 lifting points were prepared across the accessible structure. Once each section was fully cut free and prepared, 2 of the world's largest floating shear legs arrived at the wreck site. Their mission was to lift each section vertically out of the water and place it onto a nearby barge. The first section removed was the stern, estimated at approximately 3,200 tons. As the massive lifting cables gradually tightened, the salvage team observed the lifting frames emerging first from the sea surface. More than 6 months after the sinking, the submerged Tricolor began to reappear section by section. The lifting operation proceeded slowly to allow seawater to drain out and reduce weight. Equal load distribution between the 2 shear legs was essential to avoid unpredictable forces and sudden movements. When the section finally cleared the water, a barge was maneuvered underneath and the massive block was lowered gently onto its deck. On Christmas Eve 2016, the cargo vessel Cabrera ran aground on the rocky coastline of Andros Island in Greece, causing the hull to break apart and the ship to sink to a depth of about 34 meters. Immediately after the incident, Smith Salvage, together with its Greek partner Megatugs, mobilized to the site to prevent environmental pollution. As a first priority, the response team removed all recoverable oil from the wreck to avoid leakage and then salvaged a portion of the cargo that was still accessible in the initial stage of the operation. After stabilizing the site, the same partnership was awarded a follow-up contract to undertake the complex task of removing the stern section, including the accommodation block resting on the seabed, as well as the remaining cargo fragments trapped within the structure. For this phase, the project relied on the heavy Boscalis floating shear-leg crane TAC Lift 4, which provided the lifting capacity required to safely handle large submerged steel components under challenging underwater conditions. By October 2017, the entire wreck removal program had been completed successfully, demonstrating coordinated effort, advanced marine engineering, and strict environmental protection measures throughout the salvage operation. On the 5th of December 2012, the car carrier Baltic Ace collided with the container vessel Corvus J in the North Sea, about 65 kilometers off the Dutch coast. The ship sank within only 15 minutes, and sadly, only 13 of the 24 crew members survived. The 150-meter vessel came to rest in one of the busiest shipping lanes leading to the port of Rotterdam, creating both navigational and environmental risks. In 2013, investigations showed that the wreck threatened safe passage and contained nearly 540,000 liters of oil, together with over 400 cars whose fluids could potentially leak. Consequently, complete removal of the wreck was considered the only safe solution. In March 2014, the Dutch authorities commissioned Boscalis and partners to ensure a clean seabed before the end of 2015. Because severe winter weather prevented year-round operations, the works were split into two phases. First, the oil was removed through a special hot tap technique that heated and pumped out solidified oil, with more than 456,000 liters extracted. Divers then cut access holes for later lifting and assessed internal damage, revealing that the hull was too weak to be removed in 6 large sections as initially planned. From April 2015, a specially engineered wire-cutting system began dividing the ship into 8 sections. 2 floating barges with a heave compensation system allowed precise cutting despite waves. However, the separated sections deformed on the seabed and required tailored lifting solutions. The stern and bow were lifted first in single pieces, while weaker parts were removed using a large salvage grab. Despite summer storms, the last large fragments were retrieved by late August. Finally, debris, scattered auto parts, and metal pieces were cleared, and the seabed was scanned and cleaned. Nearly 13,000 tons of material were recovered and sustainably dismantled for recycling. By October 2015, the seabed was declared clean and shipping traffic safely resumed ahead of schedule. Tank cleaning is one of the most essential maintenance operations on modern merchant ships, especially on oil tankers, chemical carriers, and bulk vessels. Cargo tanks continuously come into contact with liquid products, sediments, waxes, and sludge, which can remain on surfaces after cargo discharge. Consequently, each tank must be thoroughly washed before loading a different grade of cargo or during regular maintenance. In the past, this job was performed manually by sending crew members inside contaminated tanks, which was both time-consuming and extremely dangerous because of toxic vapors and confined space conditions. Today, ship tank cleaning machines, as demonstrated in the live video, have significantly transformed this process by using automated or portable systems equipped with high-pressure cleaning jets, improving cleaning quality while greatly enhancing safety. Modern tank cleaning machines operate using powerful pressurized streams of water, steam, chemicals, or sometimes even crude oil recycled from the tank itself. These pressurized jets strike the internal surfaces of the tank, breaking down residue, loosening deposits, and flushing sediments down toward the suction points for removal. In addition, many rotary machines use a programmed cleaning sequence, gradually covering the bottom, sidewalls, and overhead areas in a precise pattern that increases in density with each rotation. Therefore, even areas that are difficult to reach manually, such as corners or upper frames, are fully washed without requiring human entry. Most automated devices consist of a rotary jet head, internal gearing, and a high-pressure supply line. The rotary head slowly turns horizontally and vertically, producing a spherical cleaning pattern. Because the rotation follows a programmed sequence, the machine eventually covers every square meter of the tank interior. This geometry ensures maximum cleaning effect with minimum consumption of water or chemicals. In addition, automation reduces the number of machines required, meaning that several tanks can be cleaned in parallel, shortening port turnaround times and reducing operational costs. There are several common types of ship tank cleaning machines used across the maritime industry. Rotary jet heads, such as the Tofte series, are widely installed on large oil and chemical tankers. These are often permanently mounted inside tanks and are connected to the vessel's fixed washing line system. They are designed for complete automatic cycles and offer dense cleaning patterns suitable for large-capacity cargo spaces. Portable systems, such as the Scanjet SC 15 terawatts, are highly versatile and can be moved from tank to tank, making them suitable for barges, smaller vessels, or specific cleaning tasks. A third category includes single-nozzle systems, for example the Scanjet SC30A, which are specially designed for hazardous areas requiring ATEX compliance. Meanwhile, high-pressure water guns like the Polar Jet are frequently used in cargo holds on bulk carriers, sometimes mounted on tripod stands to create a stable cleaning angle. The applications of these machines are wide and include crude oil and product tankers, chemical carriers, and bulk carriers. Offshore supply vessels and offshore production units also rely on rotary jet systems for cleaning supply tanks or process tanks. Furthermore, some shipyards use similar devices for washing new-build tanks prior to commissioning or before coating activities. Using automated tank cleaning equipment brings multiple operational benefits. The most important advantage is safety. Since the cleaning process occurs externally, crew members are not required to enter confined spaces filled with flammable vapors or toxic atmospheres. This greatly reduces the chances of accidents, explosions, or poisoning. Efficiency is another major benefit. A fully automated sequence can complete the entire tank cleaning cycle in a fraction of the time required by manual washing, while consuming less cleaning media and energy. Compliance with international maritime regulations, particularly IMO and MARPOL rules, is also enhanced. Many cargo types require the tank to be washed according to specific standards in order to avoid contamination between cargoes or environmental discharge violations. Automated systems help operators maintain consistent cleaning quality and meet these environmental obligations. Finally, the versatility of modern tank cleaning machines allows them to handle various types of cargo contamination, diverse tank sizes, and different vessel categories. Their programmable cleaning patterns, high-pressure performance, and robust construction make them indispensable equipment across the maritime industry. The production of leaf spring suspension systems at APM Springs in Port Klang begins with raw material storage, where high-quality spring steel is carefully selected and inspected. Next, the steel bars are heated in a heating furnace to reach the required forging temperature. Once heated, they undergo parabolic taper rolling, which forms the characteristic tapered profile that improves flexibility and load distribution. Afterward, eye rolling shapes the spring eye for future attachment, while hot grooving creates slots that help control stress points along the leaf. The partially formed leaves then move to press quenching, where they are rapidly cooled to achieve the necessary hardness. Additional forming steps include finger press and air link press, ensuring precise geometry. To increase fatigue life, the springs are subjected to shot peening, introducing compressive stress on the surface. A spray painting line then provides anti-corrosion coating, followed by reaming and bushing to finish mounting points. Next, individual leaves are joined during assembly, forming a complete spring pack. Each assembled spring undergoes load testing to verify strength, deflection, and durability under simulated working conditions. Finally, qualified products are moved to the finished goods area, ready for delivery to automotive manufacturers. Commemorating the commissioning, the Las Bambas copper mining project marks the beginning of one of the largest and most modern mining operations in Peru. After years of planning and construction, the site has officially entered full production, capable of treating 140,000 tons of ore per day through advanced processing facilities. Moreover, the project is designed with a strong environmental focus, as 95% of the water used in the production cycle is continuously recycled, significantly reducing freshwater consumption in this high-altitude region. During its first 5 years of operation, Las Bambas is expected to produce around 2 million tons of copper, becoming a major contributor to global supply and Peru's export economy. Finally, the concentrate is transported by a dedicated logistics system to the port of Matarani, and from here it is exported to customers and industries across the world. The Doyan 16 Sea Crew operation demonstrates a modern approach to running casing directly with the rig's own personnel and equipment. In this operation, a full casing string was successfully installed into the wellbore using the rig's integrated top drive system, rather than relying on a separate casing service company and conventional handling tools. As a result, the overall process aimed to improve operational safety, enhance efficiency, and reduce both cost and non-productive time during well construction. Doyon Rig 16 is a purpose-built drilling unit operating in Alaska's North Slope, where drilling activities must be performed under extremely low temperatures and harsh Arctic conditions. Its design focuses on reliability, mobility, and strong operational performance in remote environments. In this case, the crew employed a Volant top drive casing running tool. The CRT grips the internal diameter of each casing joint, allowing the driller to make up and break out connections, rotate and reciprocate the string, fill the casing while running, and circulate or cement the well without exposing personnel to the hazards traditionally present on the rig floor. Implementing this technology required rigorous preparation. The sea crew received extensive theoretical and hands-on training, supported by equipment specialists and performance engineers from the supplier. The training ensured that the rig personnel could operate the CRT confidently and integrate the technology into daily drilling procedures. As a result, running casing became a standard operation executed by the rig team rather than an external specialty crew. This successful run is often referenced as an example of how innovative tools can expand the functional capabilities of existing rigs. By applying new technology within a familiar workflow, operators are able to optimize well construction activities, improve safety, and generate meaningful financial benefits over the life of the project.